Hello and welcome to our today's webinar about the assessment of pedestrian wind comfort with cloud-based CFD. My name is Milad Mafi and it's a great pleasure for me to be your today's host. Before we start to dive into our today's topic, I would like to introduce myself. I have more than 10 years of experience in the field of computer-aided engineering and computational fluid dynamics, and I'm currently working for 4 years as a product marketing manager at SimScale, and as a part of my role I am organizing and conducting several workshops and webinars around different topics to introduce interested users into the fundamentals of computer-aided engineering. And let's first of all take a look at our today's agenda. First of all, we will briefly discuss the general benefits of using simulation or CFD, and we will also talk about SimScale, and I will quickly introduce you to the concept of SimScale and how you can run your own simulations through your web browser using SimScale. After that, we will start to talk about our today's topic, so we will first of all discuss about wind comfort, so what are important effects and what is actually the aim of an engineer who tries to optimize the wind comfort of a building, or the pedestrian comfort, and we will also talk about how CFD can be used in this context. And we've prepared actually 3 kind of different demos today. So we have 2 validation cases, which you may also know they are quite popular, and we will show you how we created a simulation of this wind tunnel validation case, and we will discuss the results. And after that, we will take a look at a real-world project where we improved the wind comfort of the pedestrians using CFD. In the case you have questions, you can just write them into the question box, and I will try to answer them directly or latest during our Q&A at the end of the session. Yeah, let's start to talk a little bit about the benefits of simulation. And before we start to talk about CFD, I would like to discuss a more general concept with you. And this is the question, what is engineering simulation? And as most of you know, for example, CFD or fluid flow simulation is just one of a lot of different techniques which are available and which can be used to replace physical testing. And first of all, let's try to understand what's the difference between an analytical model and a numerical model. And then I think a lot of things will become more clear for you. So you all know analytical models. And for analytical models, well, there's typically a closed mathematical solution for the entire domain of the model. So if we're interested in a certain quantity, the value of this quantity is known for the whole domain, and we have like a continuous, yes, we have a continuous kind of solution. And unfortunately, this kind of models are not really available in engineering because they can only be solved for very simple problems or simple models. An example here is a linear force on a spring, where we have the known relation which says that F, the force acting on the spring, is proportional to the displacement of the spring, and the proportional factor is the stiffness of the spring. And whenever things becomes more complex, the result is an analytical model which cannot be solved analytically. So what we do is we use numerical models, which means instead of calculating our solution for the whole domain, we'll just calculate it for a certain number of defined support points, and in between we will approximate the solution. And this allows us to simulate complex problems, but it needs appropriate models and algorithms as well as the right amount of computational power. And when we talk about CFD, so about computational fluid dynamics, this is a good example for a numerical model. And the great thing about simulation is that it allows us to develop our products better and faster. And actually, there are a lot of different, let's say, advantages, and I just want to address some of the most important. So First of all, what you can say in general about simulation, that it allows you to test design correctness and efficiency at a very early product stage. And this also comes along with the fact that simulation does not need any kind of physical prototyping. So you don't need the test rig, and you also don't need to manufacture your test object, your prototype. And this results in a lot of advantages. And I just want to name 3 of them. First of all, it reduces your time's investment, because using simulation and starting to work on your on the design of your project at a very early design stage, on the one hand, will reduce the total development time in general, but also usually preparing a simulation costs much more costs less time than preparing a physical test. And usually what our customers and users do, they do a lot of simulation at the beginning of the development process, and at the end they do a kind of physical validation test. And this allows them really to reduce the return time for developing a new product or adapting a product to the needs of a customer or different market. Simulation or using simulation will also minimize the risk of failure, because a lot of times when things go wrong, it's not because people did completely let's say things which are completely wrong, or that it was obvious at the beginning that they will fail. Most of the times it's more that a small detail which was never considered suddenly changed something big. And here again, simulation plays a crucial role, because simulation is using the Navier-Stokes equation. So really the fundamental governing equation describing the motion of fluid flow to calculate a solution. So it will really consider everything which you input into the model or which you consider into the model. And a lot of times when you get simulation results which looks different than what you've expected, this can be a hint that maybe in this time you really need to take a closer look to understand the physics of your product, to see why it suddenly changed so much its physical behavior. And yes, finally, all of these things helps us in the end to reduce costs. And I mean, this is I think this is one of the most important, that's it, things, right? To reduce costs, to build a better product in a shorter time, and by spending less money. And when it comes to the AEC industry, there are some certain, let's say, very interesting applications for CFD. And first of all, CFDs can be used actually everywhere inside your building to validate the performance of single parts of an HVAC system, or even the whole system. CFD can also be used to improve the energy efficiency. And here you're actually not limited to any, let's say, heating concept. You can simulate forced convection as well as natural convection, and try to optimize the amount of energy which is used to ensure thermal comfort inside your building. Using CFD, you could also predict wind loads and simulate building aerodynamics. And this is actually what we want to do today, right? The only difference is that we will not take a look on what's happening on the facade, but how are the flow conditions for pedestrians. But we will talk about this in 5 minutes in detail. And you can also use CFD to optimize thermal comfort or to control air quality and contamination. And a lot of examples are residential in the field of AEC, but you can also use our tool, especially when it's about air contamination and quality for industrial applications, like optimizing the ventilation layout in a coating plant. All right, and from what I've told you, you must think, well, simulation seems to be a super powerful tool. And you might wonder if I tell you that only 1 out of 25 engineers currently has access to simulation. And there are a lot of different reasons. And 5 years ago, when SimScale was founded, we actually wanted to remove some of the barriers which we saw are the reason why simulation is not a standard tool today. And that was why we introduced SimScale. And before I will tell you in detail what SimScale is, let's talk quickly about the barriers. And actually all of the barriers can be summarized to three main reasons why simulation was not adapted in the past. First of all, traditional on-premise simulation tools came with a lot of initial costs and a high initial investment. You needed to buy not only the software licenses, which can be very expensive. On-premise simulation software can cost you like 30, 40, 50,000 euros a year. That's not a problem. And besides this also, accessibility was a big problem because you not only needed hardware and software, but you needed experts which are able to build up an environment, an IT and infrastructure, which you need to run the simulations, because you need a special kind of, let's say, servers, high performance clusters to solve simulations, and then you need a machine which has graphical power, for the post-processing. And the third reason, and from my point of view, that's the most important barrier, was what we called the know-how barrier. So most of the tools were not designed for the end user, how we call it. So they were not designed to be used by the design engineer, but they were made for simulation experts. And this obviously is limiting the audience for such tools. And yes, the result of these considerations was that we've developed SimScale, which is the world's first cloud and web-based simulation platform. And in a nutshell, it means you just need a web browser, a standard web browser, working on internet connection, and you can run unlimited number of super precise CFD simulations through your web browser. And SimScale actually comes with some advantages, and I just want to name some of the, I think, most important unique things about SimScale. So first of all, SimScale is what we call an all-in-one tool. So it unified structural mechanic tools, CFD tools, and tools for thermodynamic simulations. And this is a big difference, because usually all the other simulation tools, you have to pay and license every module independently. Based on, or due to SimScale cloud-based approach, SimScale is super fast and easy. And it works on every device. You can work from wherever you want, and it was much faster than, let's say, most of the on-premise solutions which are available for small companies. SimScale also comes with real-time support through chat, phone, and email, and besides this, we also offer consultancy, webinars, and training. And what is also, I think, a very interesting point for you guys is that SimScale is actually free of cost. So we have our community plan where you can test everything. The only difference to the commercial plans is that your simulation projects will be public. But besides this, SimScale is actually free, and SimScale has a lot of great collaboration features, including our community where you can join a network of more than 120,000 users and access our public projects. And SimScale at the same time, also it's using cloud technology. It's super secure since we are encrypting our data 2 times using the AES standard. Let's now talk about our today's topic. And yes, our aim today is to understand how CFD can be used in the field of pedestrian comfort, and therefore let's start with a small introduction, and let me quickly summarize what you're going to learn in the next 20 minutes. So as you know, especially in urban areas where we have a lot of large buildings and a high density of buildings, wind effects can happen, which means that if, let's say, a small breeze with several meters per second of speed get amplified, for example, through cross-section changes, and then we have high velocity peaks, which can be quite dangerous for pedestrians. And here's a video which really illustrates what this means for people who are walking around. So this is like a breeze which is even not as fast as it seems, but people are really struggling to cross streets. And this is, yeah, in some regions this is a big deal. And what is used to characterize wind forces is the so-called Buffon scale. And it's categorizing winds or breezes based on the wind speed at 1.7 meter above the ground. And the fact that we are measuring the wind speed 1.7 meter above the ground is quite important, and we will talk about this later. And however, based on the wind speed, we have different strengths in BF, and even 7 to 6 to 10 meters per second, which is like 40 kilometers per hour, is kind of critical and strong. And now let's first of all quickly talk about some of the most important wind effects and then try to see how they can be modeled using CFD. And yes, maybe the most important effect when it comes to wind comfort is the Venturi effect. And the Venturi effect actually is also called by some people the Bernoulli effect. Also, Bernoulli effect is something more general. However, what is happening is that whenever the wind is crossing a constricted area, like you can see in this example, so that the cross section get reduced, the velocity increases and at the same time the wind pressure drops. The wind pressure actually drops because the velocity is increased. You need to get your energy from somewhere. And as you can see, this is quite dangerous because if you're like walking, let me try to take a pointer like here, let's say, and then you are like walking like a little bit to the left, you suddenly get hit by a speed difference of like 10-15 kilometers per hour. And yeah, this is something which actually happens in every larger town, but most of the times it's not super critical as long as the wind speed is not as high. Also, an effect we can observe in urban areas is the flow separation at the building corner. And what is happening is that pressure differences between the front of the building where we have high pressure and the sides where we have low pressure, that this pressure differences creates lateral vortices. And you can see one of the vortices here or here. And this is also a problem because it can really decrease the comfort in the regions where you have a lot of turbulence. And not an effect which is not very common, but which can happen if you have such a design, is called the jet effect. And it's actually happening in passages. And let's say we have like two buildings and the ground floor is kind of open, it's a passage. Then it can happen that we have such kind of jets. It's a little bit similar to the Venturi effect, but actually more the other way around. The Venturi effect is that we have a high speeds, so it's a kind of special case of the Venturi effect. And then we have like this one very fast and strong, what is called jet. And yes, if you like walk through it, this can be quite dangerous in the case that you have like higher wind speed. And so using CFD's idea is that we can simulate what is actually happening and identify such flow phenomena which we want to avoid. And a question which is raised a lot of time is like, how can we test it? And well, there are two possibilities. One is to do a wind tunnel test. The other is to do a simulation, because building a prototype city usually is not an option. And since a lot of people were asking about the accuracy, we have prepared a kind of validation study where we've taken the validation results provided by the Architecture Institute of Japan. And now I would like to share two of the cases with you. So the first one is a case D from the set of validation cases. And this is a kind of turbulent steady-state wind flow around a single high-rise building in Niigata. And this single high-rise building is surrounded by blocks of simply white low-rise houses. And what we want to do now is to actually simulate the flow around the city and then to compare the results with the experimental results provided by AAJ. And first step creating a simulation is what we call meshing. So divide your model into small cells, and in each of the cells later we are calculating as wind velocity. And we created like a bounding box of 1.8.1.8.1 meter. And since we are like simulating the wind tunnel test, it's also a scale model used for the simulation. And something which you can see here is that we like used a refined mesh in the near of the floor to resolve the boundary layer and capture the properly capture the flow near the ground. Yes, and here you can see some of the results. So the colors are representing the normalized velocity, and red is the highest velocity in the domain, blue the lowest. And this is like, so on the left side you can see like the characteristic flow pattern around the city, and on the image on the right side is showing a section. And what we did is that we, added some points from based on coordinates, and every point was labeled from a number from 1 to 78. And we used the normalized velocity, which I mentioned was used which we calculated by using a reference velocity of 7 meters at the building height. And now what you can see on the left charts are the results from the experimental wind tunnel test compared with our simulation. And as you can see, it's actually not very far away. So and for a lot of points, the trend is absolutely right. It's a little bit off for sure, but you should not forget the simulation, and therefore we are not only interested in the quantitative values or quantitative results, but in the qualitative results. And there it's absolute great, like all the peaks are captured fine, and even for like, or especially for high degrees of wind direction, if we take a look at the lowest one, it really looks nearly perfect. Now let's take a look at some streamline visualization. So the streamline filter is used to visualize some flow patterns, and here you can see like how the flow is going around the building, and also how this vortex is formed because of the pressure difference at the side of the building and the back wall. And on the image on the right side, it's the same thing from a little bit different perspective. We also have a second case from the AIG case library, which we've prepared today, and this is a steady-state simulation of a turbulent wind flow around complex buildings with simple building shapes in an urban area. And it's again from Niigata, so the author. And yes, we used in this time a full model and a full geometry with a fluid domain of 1 kilometer in x and z axis, and an x and y axis, and a height of 250 meter in y axis. So this is our small city. The red building is the detailed one, and the wind is coming from north. On the right side you can see the boundary layer profile provided to our model, and this is very important, and one of the unique features of SimScale is that we support atmospheric boundary layer conditions. And if we take a look at the mesh, here we can really see the strengths of the cloud-based approach of SimScale, because it allows you to create a very high quality mesh with a lot of cells through your web browser. And yes, again, we use layer elements and refinements on surfaces and whole regions to adapt the mesh to our needs. And finally, the total number of cells is around 30 million for this case, which is a quite high number, so it's something you would not be able to handle anymore on a computer or a single workstation. And now let's take a look at the results. Again, we added some probe points, and you can see below, and you can see the experimental results versus our simulation results. Again, we are pretty close to the measured results from the wind tunnel. And you can also see the flow pattern here and how like some jets were resolved and some other effects inside the city. Different visualization here we use again streamlines as well as surface streamlines on the plane to visualize both the three-dimensional and the two-dimensional pattern of the flow at different heights. Yes, and finally we've also prepared, let's say, a wind study of a building project from the real world, and this is from one of our base of a problem which was optimized by one of our customers, and he wanted to add some natural barriers to increase the wind comfort in the dining garden area of a restaurant, and therefore the guest comfort is measured 1.5 meter above the ground. And the idea is that you arrange the small trees, which were modeled as porous medias, in a way that you reduce the wind speed at 1.5 meter above the ground. Yes, so this is geometry, and first of all we created the simple parametric mesh. And here you can see again we added some refinement as well at the building surface area as well as to the edges, and then we created a little bit a second mesh where we additionally added for the trees some dummy models, and this trees itself were grouped the cells to porous zones so that we can really consider that they are not walls but trees. Yes, regarding the measurement location, again we defined a local coordinate system and some probe points. And the wind arriving from the backside of the restaurant has an inlet velocity of 3 meters per second, which is a light breeze. And the recommended airspeed in contrast to that for while eating or being seated is 0.2 meters per second. And yes, therefore we used this measurement setup to judge about the wind comfort improvements. Here you can see the results. First of all, let's compare the wind speeds. And here you can really see how this big jet, which was formed before between the dining garden and the beginning of the restaurant itself, was completely avoided by using the trees. Actually, it seems like the flow velocity inside the garden is everywhere very, very low. And if we now take a closer look, we can really see the effect of the tree. So it's actually like a grill in a car a little bit, and you can see how much the wind speed was reduced in the dining area from something around an average 2.5 meters to like 0.4 meters per second. Yeah, again some visualizations. So here you can see the streamlines, and actually it shows how air is like sucked down by the trees, and you can also see like how some vortices are created at the edges of the roof. Yes, and now finally I would like to show you quickly just how such a simulation looks on the SimScale platform. So therefore let's switch the browser tab. As you see, I'm just in a standard web browser, and I will open the project now, and this is, for example, the validation project. So as I mentioned, we have 3 steps. The first step is what we call the CAD import, and therefore you need to prepare your CAD model, and then you can upload it to SimScale. And in this case, we provided the models using the STL file format. So there was like one single surface for all of the buildings, but you can for sure also like create separate patches for each building, and you can even split geometries and scale them. on the platform. And here we use the split operation. Yes, then for creating the mesh, we have several fully automatic and manual solutions. And the final step is to actually set up the simulation itself. Everything is happening inside our new Workbench 2.0, which makes working even much more straightforward and simpler with SimScale. Yes, and as I mentioned to you, the second step is to simulate everything, and then finally we do our design decision based on the project. Yes, thank you very much for your time, and it was a big pleasure for me to be your today's host. In the case you still have some questions which were not answered on the chat, just drop them. And yes, you can also reach out to me by email. My email address is mmurphy@simscale.com. All right, thank you very much. It was a big pleasure, and I hope to see you soon. Bye.